the profile where each node's there, and then it's the other node. Well, this is no longer the scale at that point, where it's a node down there and the other nodes, that they calculate that, well, that no matter what, that they're never going to be more than 160 kips on there. Now, I've had people write me, engineers write me and all that, tell me they're 280 kips per linear foot and all that. Well, obviously they didn't think so, because they only are addressing a very minimal amount in the transverse cables. And I'm using the transverse cable as my weakest point of this. Looking at, I'm going to show you that, and then so you guys can find all the data yourself. These are the plans. I'm going to show you what I'm talking about, that spacing. So there's the spacing of the backspan. Alright, so here's the spacing, and if you come down here and you look at the plans, you'll see 2'6", 2'8", 2'8", 2 foot. It's 2 inches. Alright, and you look at the first one, I believe this is 10 members over, and at the 15th, let me look at my notes, I actually wrote that down. 15th and 14th one, and then you count over, this is now like yeah, let me look at my, I wasn't ready to see my notes, they're in order, and I wasn't ready to jump to that one, but let's keep it for video balance. Let's do that. So yeah, I have a 14 and 15, so somewhere about 14 and 15. Then the next one over, the next node over, I have it at 13, 14, and 15. Oops, sorry guys. So I believe this is the next node over. I have it at 13, 14, and 15. And look at 14, dead center of it. So right there, that's got, you know, if you think about the load forces, it's taken on the most, and that's a little less. If you can free body diagram it that way. Now, if you could make this concrete act as a plate, the entire thing act like a plate, like a truss plate, or I'm trying to think, like a footer. If you can make this entire top of this, everything above the reinforcement act like a footer, that means you put a load here and it transfers on an entire area zone equally, which it doesn't really do. So I just can't get it. I can't get it to do that. I'm trying to make it work, and I just find it so mathematically chaos. All right, the next one is 11, 12, 13. So you count over from this one, you get to 11, 12, and 13. 11, 12, and 13. Looks like 12 is center. And then you go over again. Now you could check my numbers on this. I could be wrong. Next one is 11 and 12, straddling it. So you count from here, you come over 11 and 12 tendons, and now you're straddling it on each side. The point being is that that's an imbalance too. So there's 12, 11 between that one, there's 13 between this one. This deck is not in equilibrium. Now you add the weight of the bars, what you got above us, the steel pipes, and that changes everything again. Those steel pipes are much longer out here than in here, the closer to the pier. Closer to the pier, that would be that one there. That's a shorter pipe. That's a longer pipe, that's a longer pipe, and an even longer pipe, which is even more loads. Hopefully the loads start working over there. This is just so whatever. Alright, so there's the transverse cables will be buried in here, and I believe they're above, as you see here, above the reinforcement, and above the transverse cables, or above the longitudinal cables, and the deck, the wiring, the fabric, not fabric, the 6x6. I think it's 6x6. It could be anything. 8x8. I don't think it's. I don't know. It could be larger. But this is what that's that transverse tendons, and this is what I see could be an imbalance causing that torque in that deck also. All right, so you do the math of how much torque that would create if you add them all, the post tension from one side all the way down, and don't flip. I'd love to see that detail. All right, going back to the notes. Further loading was not done with shims, right? So when they test loaded this product, they did not load it with. When they test loaded in the staging area, as I call it, the impound, which I take this a lot more seriously now. I guess I should not call it the impound anymore. That they did not have. They had a brace on here also. Braces on the side of this. This, I believe, might have had some wood shims underneath of it, so that would have given that transfer of loads. But they test loaded this in the impound, if you will, after it's already been grouted, and 2 and 11 still post tensioning, remain post tension. They didn't detension it in the testing area. Okay. Cracks are from false works, not an engineered foundation. Okay. Why? $12 and $11 because the node. Okay, right. I talked about 12 and 11. Why it broke here is because it acted like a node. Why it broke there and there. Those are the strongest points of the loads. Never making it. I mean, these loads never made it out to this diaphragm. These loads somehow were double backed to this node here, which came down to here, and presented itself here and here. But again, this was at the beginning of the whole design, because we had that small crack. It's right here. That small crack to me tells me this whole thing is dipping down. That one crack is the one. One crack that tells the whole story. All right. And then you look for the story why it's doing that. For example, there's this too wide here. Is it 10 foot and 9 foot 10 on that side, etc. And then when you compress it, you've got the forces coming down. Evenly spaced transverse cables. Did not care where the deck loads were. Right, so they went from 2 foot 6, 2 foot 8. It's just, it didn't matter. It seems like you could put this anywhere you want in their design. Once they did the deck, they're like, it doesn't matter. You can load it anywhere you want. You know, if you got to move this over a few inches, no big deal. We won't move the transverse cables to help these loads transfer out to the diaphragm. We don't have to worry about that. We just space these evenly. We'll just put these 2 foot 6 and 2 foot 8 all the way down the structure, and whatever loads you put on it will automatically go to these guys, which will then go to the diaphragm. That was their, I believe, their intent. I don't see it that way. Bonded grout, right. I don't see bonded grout happening at this time either when they did number 11. There was no transverse cables, guys. Remember, there were only D1. This guy, I showed that in a previous video. Only D1s were done. So all the loads that were in D1 went back to the deck. The voided, ungrouted ductwork of D1, I believe, could have caused cracks in the deck right then. That could have been the cracks in D1 right then. You'd have to do the math to see if the reinforcement could resist it. The steel reinforcement, the mat, along with the whatever D1 could offer at that distance. Okay, D1 70%, right, but early failure over D2 and D6. So D1 is only, the post tensioning in D1 is only, let me look at the notes here. Post tension in D1, they're only, remember, they're only at, the kips on D1 is two different ends, right? It's 471 and 489. 471 and 489. 471 is down there. That's the weaker end that we've got the failure on, and 489 on the distance further away. This end of the structure is just inherently weak under post tensioning. Then D2, D6, they're showing as remember, you got zero margin of error in this too. They want them zero. No wobble, no friction. Everything must be zeroed. That's a 745 and 775. So 745 kips on this end and 775 kips on the other end. Did I just say that numbers right? So again, this makes this whole end of the bridge inherently weak. Concrete could not take 2 cycles, so it couldn't take the 2 cycles of tensioning and post-tensioning of this. They had 1 cycle where they post-tension it when it was over there, cycling, putting a load here, detension, cycled again at the time of failure. This time it just said, all right, we're done. We're done. Oh, too much failure has already happened at that point. It was a progressive failure that they just threw a sledgehammer at. A progressive failure. Look that up, guys. If you guys, my lovely engineers out there, that my people following this that are so advanced now, look up progressive failure. You'll like it. And you'll see that what you're looking at is a progressive failure. You just need to find where the progression started from. Everything's pretty much progressive unless it's a brittle fracture, brittle failure. All right, but it was progressive still. There was still something loading, you know, in the background, microscopically working on it, even with the metal fatigue. Okay. Transverse cables creates a continuous moment profile from out of deck to the center of deck, crossover D6. I talked about that if you're on one side, it's just, you know, it's creating this damn butterfly effect. What's the butterfly wings, I call it. I'm actually thinking of a butterfly roof when I think of it like that. I don't think of it as a butterfly. I'm actually butterfly construction roof. Bars, right? 280. Right, so they had 280 kips on it. The elongation was none because bars you just get the 280 kips and that's it. They fail at 400. We talked about that. And I am done. That's the end of the notes. Of course, I can adjust anything you guys like to adjust. I just want to not go too much down to, you know, everything that I wanted to share. This is, you know, showing you that how these cables now, I wanted to show you what it would look like with a crack between it. If this was a crack, how the load path is like down and back up again. There's no crack here, so it's a smooth load path. Here it is fully loaded if you fully cardboard, and it's again, it's sharing the loads across it. And I just made a couple of points like that. So here's a load with no wire down the middle, and I'm showing, let's see if I can see that. Oops. And you're showing the void in the middle that I'm going to put this load on, if you will. So there will be some transverse cables there, right? You figure out which one loads more, but this, you see if I push down the middle, how everything moves. Now the concrete here becomes under tension because this is more structurally sound, so that's why it's got more resistance on this side of the structure than this side in my demo. Really? Trying to see the image to make sure you can see it. Okay. So when I push here, you can see that it's more experienced on this side because we don't have the integration of all the concrete, if you will, concrete, right? Of all this. Otherwise, it would be more imbalanced. But you see what happened there is that even though the small breaks took place, it still has tension and everything holding this together. I don't know if that really helps you, that last part. It takes me a while to get this stuff worked in my brain. Look, I'm going to terminate the video. Hour and 24 minutes. I got to get my life back. I got to go back to work. I'll look at your comments on my cell phone. Please enjoy this content and subscribe. Where's my 3 people to give me my thumbs down? You know, I gave you little props just now. I'll be looking for my thumbs down. I'll expect you to be first. All right. Take care. Thanks. Bye.